The purpose of this segment is to go over some of the details associated with the peak broadening process in gas chromatography. And the central idea here is that there's a relationship between plate height and the velocity of the mobile phase. Remember, I said the important velocity in gas chromatography is UM, and so there's some function that relates the plate height to the mobile phase velocity. So if we go back to the resolution equation, which is dependent on peak width, and recognize that there's a relationship between this peak width and the plate count, which is 16 times the square of the ratio of the retention time and the peak width, and then finally recognize that there's a relationship between this plate count and the plate height through the column length. So N is equal to L over H, or H is equal to L over N. So you see, as the plate count gets bigger for a fixed column length, the plate height is smaller. And as the plate count gets bigger, for a given retention time, the peak width is smaller and the resolution is bigger. So the general themes here are that we want large plate counts because that gives large resolution, and for a given column length we get large plate count with a small plate height. So large plate count is good, small plate height is good. And so we're interested in knowing the relationship between the plate height and the mobile phase velocity because that's proportional to the flow rate. And the higher the flow rate is, the more quickly the separation happens. And so the relationship that we're going to be using, sort of a generalized form that we're going to be using, is this. We call this the Van Dienter equation. So it gives us the relationship between the plate height and the mobile phase velocity using three terms. And so what we're going to look into now is what are the details lying behind each of these terms. How do we connect this equation and our understanding of what's physically going on inside the column? So in the case of gas chromatography, I like to start here because we have the cleanest, most thoroughly understood relationship between the plate height in gas chromatography. This relationship is not so simple in liquid chromatography, so I like to start with GC. And so the plate height is here. We call it the total plate height because we can think of the total plate height as being composed of three contributions, 1, 2, and 3. So these are like pieces of the big total H. And we see that H is dependent on the mobile phase velocity in a few different ways. There's 1, there's 2, and there's 3. And we can connect these relationships to our physical understanding of what's going on inside the tube. So this particular equation we call the Golay equation. It's sort of a specific form of the Van Dienter equation, I would say, that applies to open tubular GC columns. We could also say it applies to LC columns in the case that we're talking about open tubes, but remember that's not very common at all. So our focus here is on GC. So we needed to define some terms. We have the mobile phase velocity. Remember, this is the column length divided by the dead time. We've already looked at this. The other terms here are new. The easiest ones are the radius, inside radius of the open tubular chromatography column. dF is the thickness of the film. So if this is our column and we have stationary phase on the inside wall, dF is the thickness of that stationary phase film. And this radius here is R. And dm and ds are the diffusion coefficients of the analyte in either the mobile phase, that's dm, or the diffusion coefficient of the analyte in the stationary phase, that's ds. So these diffusion coefficients are basically a measure of how fast a molecule moves in terms of its net movement, its net displacement. How fast they move in either the mobile phase or the stationary phase. The only other term here is retention factor, which we've talked about already. So the first piece we're going to talk about is this this term here, basically. And the way we think about this is that if this is our column here, so this is the column inlet, and we inject a bunch of blue molecules here that are not drawn to scale, but give the sense that we're injecting sort of a plug of these molecules in a band into the column. Then when we turn the flow on and we push these molecules through the tube by convection, so this is pressure-driven flow, these molecules are carried by the moving mobile phase. What we know from experiment is that the molecules near the wall of the column move very slowly. In fact, molecules right at the wall basically have a velocity that's zero because they're stuck by adsorption to the column wall. Their velocity is zero. On the other hand, in the center of the tube, where the fluid is moving the fastest, the velocity here is 2 times the average velocity. So if we look at all the velocities across the cross-section of the tube here, we have high velocity in the middle, low velocity at the wall, and so if we take an average, we get an average velocity, and what we know is that the molecules at the center of the tube are moving at a velocity that's 2 times the average velocity. And so this already is basically a terrible situation because we've gone from a band of molecules which is very narrow to a band of molecules which is very broad. Okay, effectively this turns into the peak width. So before talking about retention, stationary phase, any of that stuff, we see that because of what we call laminar flow or parabolic flow, meaning that there's a distribution of flow velocities, we get broadening of the peak that we inject as a very narrow band. So this is bad. And we refer to this broadening as axial dispersion. Dispersion in the sense that the peak is spreading out, and axial because it happens along the axis of the column. Now, it's not quite that bad because it turns out that diffusion helps us in this case. So we start with this very bad situation that we talked about on the last slide where they have this parabolic shape to the flow and we have a very wide peak. But those molecules are free to move radially in the column, and so this particular molecule here can move toward the wall or it can move toward the center. And so on average, the molecules that are moving fastest in the middle of the tube will move away from the high velocity stream by diffusion, and the molecules at the wall will move away from the wall, away from the zero velocity regime into a regime that's higher velocity. And the net effect of that is that the broadening is less severe. So our peak width has gone from this wide to this wide. And this happens because molecules can radially diffuse to basically move from one flow velocity regime to another. And so this first component of H here accounts for this mathematically. And what it says is that as the flow velocity increases, the average velocity, this H gets bigger. In other words, it gets worse. Remember, we want small h. Also, as the diameter of the radius of the column itself becomes larger, h becomes larger, which is bad. And as diffusion of the analyte in the mobile phase becomes larger, h becomes smaller. In other words, the faster these molecules can move radially in the column, the less bad this particular problem is. And then there's this sort of factor to account for retention here, indicating what happens to this H term as retention increases. And we're not going to talk about this at all. I just put it in here for completeness. Okay, so this is sort of the physical explanation of the first component of H that we're going to talk about, which is the axial dispersion case. Now, if you don't believe that this parabolic flow profile happens, this is a very beautiful picture that was obtained in a small capillary, so 100 micron inner diameter capillary. And what you see here is that initially there's a very narrow band of fluorescent dye molecules injected into this capillary. And if we apply a pressure at the inlet of the capillary, we see that this parabolic flow profile develops, as shown here. And so the highest velocity of the fluid is in the middle, and at the wall the velocity is essentially zero. And what's shown over here in this set of pictures is sort of the analogous process under conditions where we don't have pressure-driven flow, and we're going to talk about that later. But for now, this set of pictures is sort of the visual evidence for this phenomenon we refer to as laminar flow. So that's one part of H. Now the second part of H is what we call longitudinal diffusion. So this is the picture we ended with in the last slide, where this band has sort of intermediate width. But now we recognize that molecules are also free to diffuse along the axis of the column, not only radially, like we talked about before, but also axially. And so diffusion in this case now is bad because we go from a peak that's this wide to a peak that's this wide. And this is because all the molecules in the profile can move randomly along the axis of the column due to diffusion. So this is the second piece of H. We say that it's, again, due to longitudinal diffusion. So if we look at the terms here, we see that as expected, as diffusion increases, as dm becomes larger, this part of H gets bigger, which is bad. And on the other hand, as U becomes larger, in this case, H becomes smaller, which is good. So remember, in the previous case, we said that here, in this case, as U becomes larger, H becomes bigger, which is bad. But now in this case, In this case now, when U becomes larger, H becomes smaller, which is good. So these two effects are kind of opposing each other. Now the last term, the third component of H, has to do with diffusion again, but now we're talking about diffusion in and out of the stationary phase. We're talking about diffusion in the stationary phase primarily. So we take the same band of analyte molecules we talked about in the last case with this characteristic width, and we imagine a set of steps. So if these molecules are small enough to diffuse into the stationary phase, which is shown in green here, in the mobile phase is in the interior of the column. Remember, there's an open tubular column with stationary phase in the walls. If the molecule is free to diffuse into the stationary phase, then while it's in the stationary phase, the rest of the band moves on. So what's shown in this picture is the band moving ahead while this molecule diffuses back out of the stationary phase. The fact is that diffusion in the mobile phase is much faster than diffusion in the stationary phase. And so by the time this molecule diffuses back out into the stationary phase where it can move, the rest of the band has been transported along the axis of the column. So we have this molecule here diffusing out, and by the time it makes it back out in the mobile phase, the rest of the band has moved on. And so now, if you imagine this occurring for several molecules, we have a peak that's even wider. So in this case, the fact that diffusion is slow in the stationary phase is the big problem. So this is the third piece of H, and so we have this relationship here. So in this case, as the mobile phase velocity becomes higher, H gets bigger, gets worse. As the film thickness becomes bigger, so this is the film thickness here. As the film becomes thicker, this H becomes larger and worse. And as the diffusion coefficient of the analyte in the stationary phase becomes bigger, H becomes smaller. So having a higher rate of diffusion in this case is a good thing again. So what we're going to want to discuss then in putting this all together is to think about sort of graphically what is the relationship between each component of H, the longitudinal diffusion, the axial dispersion, the stationary phase piece, and how are they related to the mobile phase velocity. So we'll put those pieces together, and then we'll finally assemble this into what the Van Deventer curve looks like in the case of an open tubular GC column. And then we're going to discuss sort of the consequences of this relationship and how we can optimize GC columns for the best performance.